Hi everyone, welcome to week 9, almost at the end. This is where sort of all the knowledge that we've learned, hopefully my constant badgering of you doing with regards to intermolecular forces will hopefully pay off. So we're going to look at functional groups that change the chemical characteristics of the hydrocarbon and how we can test for them. So the functional group being part of the organic compound that gives it its chemical characteristics. So we've looked in the previous, we've looked at boiling point, volatility, and solubility. Now we're going to look at the reactivity of different compounds and how we can test for them and utilize this reactivity to test. So alkanes, carbon-to-carbon single bond. Alkenes, carbon-to-carbon double bond. Alkyne, triple bond. Alcohol has an OH group. Haloalkane has an alkane with a halogen, so fluorine, chlorine, bromine, or iodine. Aldehyde has carbon to oxygen double bond with a hydrogen on the end. Ketone, carbon to oxygen double bond as well. They're a bit hard to distinguish between these two. Carboxylic acid, carbon to oxygen double bond, and then an OH group here, or a hydroxide group. Ester is COO, carbon to oxygen double bond, carbon to oxygen single bond. Amide has carbon to oxygen, nitrogen, hydrogen. Nitrile is carbon with a triple bond to nitrogen, and an amine has the ammonia attached to the main carbon chain. If you're studying organic chemistry or you're doing year 12, get that tattooed backwards on your forehead so it's all you see when you look at them. So, how will we name this compound? Well, we know it's a saturated hydrocarbon and it only contains single carbon hydrogen bond, which is trying to do it, so one problem. It's an alkane because it has only carbon to hydrogen bonds. How else do we name it? By the longest continuous carbon chain. So what would this be? So the previous one will be alkane. So what would this one be? Would be a carboxylic acid. So the name ends in oic acid, and it has 2 carbons, so it'll be ethanoic acid. This is an isomer. Or you can put 1, 2, 3, 4, 5. It has a double bond between 2 carbons. So it would be pent-2ene. And if you remember, what I've been saying this entire time is the intermolecular forces determine everything. Just trying to cover the bottom. Okay. And it's all to do with the polarity of the molecules. So if the electronegativity difference between 2 atoms is less than 0.5, it is considered insignificant and not polar. So carbon to hydrogen is 0.4. So hydrocarbons themselves are non-polar. They do not dissolve in water. try and dissolve oil into water or petrol into water, and it won't happen. So if we have a functional group where carbon is bound to oxygen, the electronegativity difference is 0.8. What does that mean? It means that oxygen is going to hog the electrons that are being shared. So the oxygen is negatively charged, the carbon is positively charged. So that's why we have, it's called polar, because you have a negatively charged pole and a positively charged pole. So ethanol, you can tell that because it has an OH group and 2 carbons. The ethanol contains, the OH group, and the oxygen has the highest electronegativity. So it attracts electrons from both the carbon and the hydrogen. So this molecule becomes polar because it has points that are negatively charged and points that are positively charged. So carboxylic acids, the oxygen here is attracting all the electrons from here. So the hydrogen here will be positively charged, and the oxygen here will be very negatively charged. And this bonding and this uneven distribution of electrons is what makes carboxylic acids have such a high boiling point. So the carbon always forms 4 bonds. And as a whole, when you're looking at the functional groups, there will be non-bound electrons or free electron pairs that will go to the highest electronegative atom on the molecule, which is oxygen, nitrogen, or fluorine. So this is looking at carboxylic acid. It has a double bond to carbon, so it will share 4 electrons with carbon, but it won't share them evenly. It will steal them. Sorry, it won't steal them. It will hog them because it has a higher electronegativity than the oxygen. So it has this unequal share. So we're looking at how does this polarity or uneven distribution of the electrons affect the reactivity of an organic compound. And how can we utilize that reactivity in order to test for them? So, fairly simple one here. Carboxylic acid. How do we test for carboxylic acid? Well, it's an acid. If we have a solution and we're not sure what organic molecule it is, we're going to use a pH meter. And if it's acidic, then I think it's fairly obvious that it will be a carboxylic acid. Ethanoic acid is what makes up most of vinegar. This is going to be a really quick video, but I think I'm going to do a bonus one at the end. So, amines, natural bases. So if you want to test for the presence of amines, do this with a pH test. If it has a basic pH or above 7, then it's pretty confident that there are amines. Alcohols, so it depends. So the primary alcohol is, it comes off the first carbon. Secondary alcohol, it comes off the second carbon. Tertiary alcohol, it's on top. So some of the alcohols that are primary alcohols, you can drink and ingest. Change it to a secondary alcohol, and it makes you blind. So it significantly significantly changes the properties of the molecules, dependent on where the carbon is, depending on where the bond to carbon is for the hydroxide group. So you may have done this at school in grade 11 or 12 for your organic chemistry, but the acidified potassium dichromate or potassium permanganate reacts with the alcohols to cause a color change. And I might find have a look on YouTube for a video of this. And the reaction and the color change depends on which alcohol you're looking at. Primary alcohols form a carboxylic acid. Secondary alcohols will react to form a ketone. But tertiary alcohols will not react, so they will stay this yellow color. So propan-1-ol, propan-2-ol will both change color because you're changing the functional group. Whereas the tertiary alcohol, it will not react. So alkenes, I don't know if anyone's ever seen bromine. Anything that's got bromine in it, you should stay away from. So we take an alkene and we add bromine, which is brownish red. So when there's bromine free in the sample, it looks like pure death. If we add an unknown substance that happens to be ethene with a double bond, and we'll learn about this in the next session, which I might upload. I might do today or tomorrow. Just get it done, sort of put it all there. We'll react to form halo alkane, and because the bromine attaches itself to here, the double bond between carbon and carbon breaks, and we lose that color. The color changes. So that was much quicker than I thought. What is the time? I might just do weeks 9 and 10. Okay, so that was week 9. It's relatively short compared to the other weeks. I'll upload week 10. I might do it tonight. But yeah, I'll get it up straight away. Thank you.